In this video, we'll introduce small signal models of the MOSFET and use them to perform small signal analysis of a MOSFET amplifier. We begin with a simple NMOS transistor whose source is connected to ground and with a voltage source connected at the gate. The voltage source connected in the gate has two parts, a DC operating point part, denoted by this all uppercase symbol VGS, and superimposed on that in series a small signal component, denoted by the all lowercase VGS. As long as the gate source voltage exceeds the threshold voltage, this is going to give rise to a drain current, shown here ID. Although we haven't explicitly shown what the drain is connected to, let's assume it's connected to some circuit so that VDS is definitely greater than the overdrive voltage applied to the MOSFET for any voltage excursions that we see at VGS. So whatever circuit is connected up there, this condition is maintained, and as a result, we know that as long as the transistor is on, it will be in saturation. Subject to this assumption, we know that the transistor's drain current observes the square law. And that's written here. We've used the simple square law here, neglecting the term for channel length modulation, just to keep things simple for now. And we've written VGS in terms of its DC operating point part, and the superimposed small signal lowercase VGS. Now if we expand out the squared term here, we end up with this longer expression. Now a key point is that if we can assume that the small signal all lowercase VGS is quite a bit smaller than the term all uppercase VGS minus VTN, that is the operating point overdrive voltage, all uppercase VOV, then in such cases this third term will be negligible compared to the second term. So in this case, we can approximate the square law with the simplified expression consisting of only these two terms. This condition here is therefore the condition that's required to make use of the small signal approximation. Essentially, it linearizes the voltage current relationship of the MOSFET, since you'll notice in the simplified expression there's only a linear term in the small signal VGS. There's no longer a squared term. This allows us to perform linear circuit analysis with respect to the small signal VGS. If you don't follow that yet, don't worry, we're going to go through this again. But the key point for now is to note that this is the condition to ensure that a linearized small signal analysis is possible. The small signal VGS has to be a lot smaller than the overdrive voltage VOV. Now the drain current that results here can be thought of as having two parts. A DC operating point part with all uppercase ID, and a small signal part, all lowercase ID. And you can clearly see those two terms in this expression here. Here's all uppercase ID, the operating point, and you'll see that it depends only on the operating point gate source voltage, all uppercase VGS, and then there's the small signal component, lowercase ID, which depends on the small signal applied gate source voltage, all lowercase VGS. So you can think of the operation of the circuit as being a superposition of the operating point and the small signal. The applied all uppercase VGS is shown here on this IV plot, and its value determines the operating point drain current, all uppercase ID, according to our square law. That establishes the DC operating point, or quiescent operating point, labeled with a Q here. Then superimposed on that, we see the small signal, all lowercase VGS, which can vary with time. For example, shown here is a triangular waveform. As VGS varies around the operating point, the drain current slides back and forth along this quadratic curve, resulting in a current waveform, ID. The current waveform can be thought of as consisting of the operating point part, and superimposed on that, the small signal, all lowercase id. Now you can see here that the approximation we made in neglecting the third term in this expression at the top left is simply to assume that in the vicinity of the operating point Q, this curve looks like a straight line. In fact, we're specifically assuming that the curve can be well approximated by a tangent to this quadratic curve taken and evaluated at the operating point Q. So if this approximation is valid, then the small signal waveform applied at the gate is not distorted at the output. It's simply amplified by the slope of this tangent curve. Now, the conditions under which this linear approximation is a close approximation to the actual curve is this condition here. VGS has to be a lot smaller than the overdrive voltage. The overdrive voltage is the DC operating point value separating VGS and the threshold voltage here. This then is the basis of all small signal analysis. We first establish an operating point, and then we make a linear approximation at that operating point in order to allow for linear analysis. And as long as the superimposed signals are small enough, we can use the linear approximation to relate deviations in voltage and current away from the operating point at various points in the circuit. So again, here's our approximation valid for small signals VGS. Label that small signal. Remember, it's got to be less than the DC operating point overdrive voltage for this approximation to be valid. And then we're left with these two terms, the operating point here, ID, and the small signal here, ID. So if we write out the expression that relates only the small signal components of ID and VGS, we end up with this. Maybe handy to use shorthand VOV here. And here you clearly see the linear relationship. And we're going to define the constant of proportionality, lowercase gm. G is the letter we usually use for conductance. The lowercase g indicates that this is a small signal conductance, and the M indicates that it's a mutual conductance because it relates the voltage over here to the current flowing over here in the drain. So this schematic here captures the relationships between the small signal quantities VGS and ID pictorially or schematically. We show a voltage-dependent current source here that gives us our small signal drain current, draws that current into the drain and out the source. In the gate, there's no current flowing, neither in the operating point analysis nor in the small signal analysis, because it's a MOSFET, and so there's truly an open circuit there at DC. So a key point to keep in mind is that this picture here, this so-called small signal model of the MOSFET, depends on the operating point. Specifically, the value of GM is related to the operating point overdrive voltage, as we've shown. So before we can perform a small signal analysis of the circuit using this small signal model, we need to find the operating point and therefore find the value of Gm. Once we do so, we can replace the MOSFET with this small signal model and perform the analysis considering only the small signal components, lowercase VGS, lowercase id, having already solved for the DC operating point, uppercase symbols. I think an important point to keep in mind here is that this small signal model is just a pictorial representation, a schematic representation of the linearized equations that relate the quantities ID and VGS. It's only to be used for the analysis of the small signal quantities in the circuit. It should never be used during operating point analysis. We're going to go through the step-by-step procedure for making use of this model in the analysis of a MOS amplifier. Here we've completed the NMOS amplifier circuit by connecting the resistor RD to a supply voltage VDD. As long as VDD is a high enough voltage, we can ensure that VDS is greater than the overdrive voltage applied at the gate. Now we've applied still at the gate both the DC operating point, all uppercase VGS, and the small signal lowercase VGS. And as we've seen, this will give rise to two components of drain current, operating point part and small signal ID. The resulting drain source voltage, which is the output of our amplifier here, is simply VDD minus the voltage drop across RD. That's RD times ID. Now we can express ID as the sum of its DC operating point and its small signal, and we can keep going here. And recognize that the quantity VDS, the output of our amplifier, also can be thought of as having a DC operating point part, all uppercase VDS, and a small signal part, all lowercase VDS. The operating point part is here. You see that it can be calculated just from DC operating point quantity, all uppercase ID, whereas the small signal part depends on the small signal lowercase id. Now we've just showed how the output, having an operating point, a small signal part, the small signal component is related to the small signal drain current, a lowercase id, as shown here. You may recall that the small signal drain current, in turn, depends on the small signal gate source voltage. It's Gm times VGS. So now we have an expression that relates the small signal part of the input, VGS, to the small signal part of the output. We can write the ratio of these two. It's just Gm times Rd. So this is the gain that relates the small signal input to the small signal output of this amplifier. As usual, we'll denote the voltage gain of an amplifier with A and a subscript V. We use a lowercase v just to remind us that this is a small signal voltage gain. Now this linear relationship only holds between the small signal parts of the signals, lowercase VGS and lowercase VDS. The operating points are related by the square law. So you can see some example waveforms over here on the right. Remember that VGS is composed of a DC operating point, and superimposed on that we've got the small signal, lowercase VGS. In this case, it's a triangular waveform with a certain amplitude, uppercase V. Now remember, in order for this small signal linearized analysis to be accurate, we need to make sure that the deviations away from the operating point, V over 2, are a lot less than the overdrive voltage. The DC operating point overdrive voltage is uppercase VGS minus threshold voltage VT. So that being the case, then at the output VDS, we expect to see the DC operating point, all uppercase VDS. And superimposed on that, we've got the small signal time varying all lowercase VDS. And it has the same wave shape as the small signal VGS, but it's amplified. Its amplitude, instead of being a peak-to-peak amplitude, instead of being V, is V times GMRD, which is our small signal gain. Actually, our small signal gain was negative GMRD, so you'll see that the troughs of the input correspond to the peaks at the output. So, again, this simplified linearized analysis is predicated on a couple of assumptions. The first we mentioned already is that the applied signals are small enough to keep the linear approximation valid, but we also have to make sure that the transistor remains in saturation mode throughout all these voltage excursions. So we first need to make sure that the peaks of the VDS waveform that we compute in this way are less than VDD. If VDS ever exceeded VDD, that would imply that the polarity of the voltage across RD would look like this, and that would imply some current flowing in the reverse direction through the MOSFET. So that's not going to be the case. That's not possible. So the highest that VDS can go is a maximum of VDD. That'll happen when there's no drain current flowing. So its second assumption is that VDS max remains below VDD. Third assumption is that the lowest VDS goes, VDS min, it remains at least above the threshold, at least above the overdrive voltage of the MOSFET. So this term here, VGS max minus VT, that is actually the overdrive voltage evaluated at this point in time when VDS is at its minimum. Now, since the gain of the amplifier is negative, VDS will be at its minimum when VGS is at its output. Here we've got VGS max. So whatever the overdrive voltage is when VGS hits its peak, we have to make sure that VDS never drops so low that it's below the overdrive voltage at that point in time. If it does, the transistor enters triode, and all the assumptions upon which this linearized analysis are based, specifically our assumption about GM here, will be invalidated, and so the predictions we make based on that assumption will not be valid. In reality, what would happen is that the waveform would start to distort at this point in time. We wouldn't see a nice triangular waveform. It would be essentially the voltage is reluctant to go as far below that. The voltage current relationship of the MOSFET changes, and so there's a kind of a saturation effect on the output of the amplifier at that point. So these then are the three assumptions to make sure this linearized analysis is true. Two of them are basically just assumptions to ensure that the transistor remains in the operating point, in the operating mode we assume, saturation. And this assumption here is our small signal assumption. It's basically required to ensure that a linear approximation to the nonlinear IV characteristic is fairly accurate. So as long as you understand the assumptions upon which small signal modeling and small signal analysis are predicated, and you're careful to only apply it when it's valid, then you can adopt a pretty cookbook approach to doing small signal analysis. So let's start from the beginning again with this NMOS amplifier. The input applied to the gate, VGS, with the operating point and the small signal shown here, the output taken at the drain. Now the first step is to perform a DC operating point analysis. To do this, we set the small signal input to 0. In this case, since the small signal source is a voltage, VGS, setting it to 0 is equivalent to replacing it with a short circuit. And that's what's done here. The small signal source VGS that used to be here is now set to 0. The resulting circuit should be solved using square law relationships that you're familiar with. So if the MOSFET is in saturation, we know that ID is a half Kn prime W over L VGS minus VTN squared. Again, that's assuming saturation. We're neglecting channel length modulation just to simplify the expressions for now. And we can then use that IV relationship to solve for the all uppercase VDS. It's simply VDD minus RD times ID. So we can substitute in this expression for ID and find the resulting VDS. And then, of course, we have to go back and do a check. Is the transistor actually in saturation as we originally assumed? Need to make sure, first of all, that VGS is greater than the threshold voltage. So let's take that as given. If it's not, then the transistor will be off. It'll be a pretty trivial case there. And the second thing to make sure is that the drain source voltage exceeds the overdrive voltage. That is VGS minus VTN. As long as those two are true, then our original assumption that the transistor's in saturation is valid, and we've then found the DC operating point. We found the drain current ID and all uppercase VDS. So having done that, we can now move on to the second step, which is to linearize the circuit. And by this I mean essentially take the tangent to the IV characteristic at the operating point and use that tangent as a linear approximation that relates the small signal terms, lowercase VGS, lowercase ID. It's riding on top of the DC operating point, uppercase ID, and so on. So linearizing the circuit in this case really just boils down to finding lowercase gm. Remember, we showed that it's Kn times VOV. So having solved for the operating point, we know VOV. In this case, it's pretty trivial. It's just VGS minus VTN, and we find GM. Then step 3 is to use the small signal model to perform a small signal analysis. Now to do so, we remember that we've already accounted for the DC operating point. So all the DC independent sources in our circuit can be set to 0. Now in this case, there's really two DC sources. They're both voltage sources. There's all uppercase VGS. And then there's also, let's not forget, VDD. We've already accounted for that when we found ID, uppercase ID here. So that can also be set to 0. So if we do that and we replace the MOSFET with the small signal model we found for it, shown here. So we find that the source of the transistor is connected to ground. The drain of the transistor is connected to one terminal of RD. The other terminal of RD is connected to VDD, as we know, but in this analysis, VDD is set to 0 because we're just doing the small signal analysis now. And there also used to be this source uppercase VGS here, but in this analysis, uppercase VGS is also set to 0. So we end up with a greatly simplified linear schematic to solve for here. And remember now that we're only solving for the small signal quantity, all lowercase VDS. We can very easily see that VDS equals negative GM VGS, which is this current times RD. So we arrive at the exact same result we found before following this three-step procedure. That is that VDS equals the voltage gain AV times lowercase VGS, where AV is negative GM RD. So far, we've neglected channel length modulation, and we've focused on how the drain current of the NMOS transistor varies with the applied gate source voltage. But we know that even for a fixed gate source voltage, as shown here, the drain current varies with changes in VDS. So if we pick just one of these blue plots, that corresponds to a particular fixed value of VGS. Let's say this one here corresponds to DC operating point. And let's say the operating point lies here. That's the nominal value of, or DC value of uppercase VDS here. Then we know that with changes in VDS, even if VGS stays the same, we'll get small changes in drain current around its operating point value. So again, we usually denote the operating point with a Q, and this here would be our uppercase ID. Okay. Now the impact of VDS on the small signal drain current is captured by the addition of this resistance RO into the small signal model. So the value of RO is given by the inverse of the slope of the ID versus VDS curve from the last slide. So as long as we're in saturation, we would find this slope, evaluate it at the operating point, ID, and RO is 1 over that slope. And it's related to the early voltage, which is found by extrapolating this back to the x-axis, and the quiescent or DC operating point value of the drain current. Now, we use the prime here in this notation to remind us of the fact that we are using the simple square law to calculate the drain current in this expression rather than the more complicated expression that includes channel length modulation. This is a sort of second order effect anyway. The expression is shown here for RO. So again, this is 1 over the slope of that ID versus VDS curve. And you'll notice that we've used the uppercase, all uppercase symbol for VGS because we're going to evaluate this at the operating point Q. And when we find the value of RO this way, we can use that in the small signal model as shown below. So it's an extra term effectively in the small signal analysis so that now we can see that the drain current varies in proportion to VGS, and there's also a portion of it that varies in proportion to VDS. Down through here we have a current VDS over RO. So remember that step 2 of our small signal analysis was to linearize the circuit. In our preceding analysis, we did that by finding the value of GM using the operating point overdrive voltage, VOV. And now we have this extra term to linearize, the output resistance RO. Again, we do so in this expression in terms of the DC operating point overdrive voltage, VOV, VGS minus VTN. And we substitute in a little bit more complicated small signal model to complete the analysis. So here's what it looks like to include channel length modulation in the analysis of this NMOS amplifier. Again, we've connected the resistor RD here, and doing so, we've got a new relationship between ID and VDS. That is, VDS equals VDD minus ID RD. And that then is our load line, shown over here in black. It's got a slope of -1 over RD. It's got an intercept over here at VDD. And remember that depending on the DC operating point value of VGS applied, let's say it corresponds to this blue line here, then we find the intersection between the IV characteristic of the MOSFET and the load line. In that case, it would be this intersection point Q, and that's our operating point. So that would be step 1. In this case, we've done it graphically, but we can also solve for it analytically, but we have to do so using the quadratic expressions that relate voltage and current in the MOSFET. So having done that, then we linearize the circuit, we calculate GM, and RO in terms of the DC operating point values such as VOV, uppercase ID, so on. And then we perform the small signal analysis. And the equivalent small signal schematic is shown here. Again, we've set the DC independent sources to 0, VGS is 0, so we replace that with a short. And likewise over here, we've got the DC source for VDD also set to 0. And we end up with the simple linear circuit shown at the bottom right here. And we find that VDS is equal to negative GM times RO in parallel with RD times VGS, lowercase vgs. So the current here, GM times VGS, is passing through the parallel combination of RO and RD and giving rise to the voltage VDS. So very similar looking expression to what we found neglecting channel length modulation, except that now the voltage gain includes the transistor RO. So we just showed, using a small signal analysis, that the small signal voltage gain, AV, defined as the gain from small signal VGS to small signal VDS, is negative GM times RD in parallel with RO. I think it's interesting to remember how the small signal transconductance GM varies with respect to things that we have control over as designer. So far we've seen that GM equals Kn, which is the same as Kn prime times W over L, width over length of the transistor, times DC operating point overdrive voltage. Now, we can write a slightly different expression for GM, remembering that the DC drain current is related to the overdrive voltage by this expression. Now we can manipulate this expression a little bit and find that VOV is 2 times ID over Kn prime W over L, all square rooted. Okay, now substituting this expression into this first expression up here, shows that GM can be written in terms of ID as follows. So this is a second expression here for GM. We can further manipulate this expression up here to show that Kn prime W over L equals 2ID over VOV squared. Now, substituting that in to equation 1 gives a third expression for GM. That is, it's equal to 2ID over VOV. So expressions 1, 2, and 3 for the small signal transconductance of a MOSFET GM look quite different, but they're mathematically equivalent, recognizing the square law relationship. The key point to remember is that they're just written in terms of different variables. The W over L of a transistor, and at any given operating point, its overdrive voltage and its drain current are 3 variables with really only 2 degrees of freedom. If you know any 2 of these, and the transistor's in saturation, you can find the third one. So what's happening in equation 1 and 2 is those 2 equations illustrate very clearly that if you increase VGS for a given transistor, that is without changing W over L, what happens is the drain current will increase and the transconductance increases. Right? So that's clearly revealed by equations 1 and 2. Equation 3 reveals a slightly different trade-off. It seems to suggest that as the overdrive voltage goes up, that the transconductance will come down. So that seems to contradict equation 1 here. But the key point is that in expression 3, if you increase the overdrive voltage, you have to do so without increasing the drain current. So how can you ever do that? How can you increase the overdrive voltage without the drain current increasing? Well, it's because of the third part of this triangle here. Okay, the only way you can do that is if you increase VOV, you simultaneously decrease the width over length of a transistor. So this implies that you're actually using a different transistor at that point, or that as the designer, you are changing the size of the transistor while you're designing it. So if you do this properly, you can increase VOV, decrease W over L, and keep the drain current the same. And if you do that, it turns out that increasing VOV will result in a lower value of GM. So when understood in this way, then you recognize that these three expressions don't contradict each other in any way. It's just that generally equations 1 and 2 provide better intuition when you're working with a fixed transistor. That is, W over L is a constant. And at that point, you simply plug in the overdrive voltage and you get GM, or you plug in the drain current and you get GM. Equation 3, on the other hand, can be quite useful when you're designing a circuit and W over L is still a free variable. So this then illustrates the trade-offs very clearly between drain current and overdrive voltage, assuming you can make W over L whatever you want. In conclusion, the absolute best way to get comfortable with small signal analysis is to practice it. Remember the 3 steps. First, you find the operating point. Then you linearize the circuit around the operating point by finding the small signal parameters of the small signal model. And third, you analyze the linear small signal circuit.